We're back at it again in Physics 371 Online. Today, I'd like to go over a motivation and definition for a new quantity that we find very useful in our study of electromagnetism, and that is the electric potential, which we usually give the symbol V to represent. What we talked about last time involved the path independence of a special kind of integral involving the electric field. And we found that if you integrate the quantity E dot dl between 2 points A and B in space, that for an electrostatic field, the result that we get only depends on the initial and the final point, and not the path. So no matter what path you take, you get the same answer. So this is the reason that we choose to make a definition of the difference in something that we'll call the electric potential between those points. Because all that matters is where the 2 points are, not how we move from one to the other. So let's just call delta V, which is the potential at point B minus the potential at location A, and we'll set that equal to minus the integral of E dot dl from A to B. And the minus sign is involved just for consistency, as we will see later on when we deal with energy. So the electric potential itself can be defined with respect to a reference point in the following way. If O is some convenient reference point that we can choose in whatever way might seem helpful in a particular problem, then we simply integrate from that reference point to the final position R, negative E dot dl, and the value that we get is considered to be the electric potential at that point. So effectively what we're saying is that at the reference point the electric potential is 0. Now note that the original equation above only defined the difference in electric potential between 2 points. And so this defines an absolute expression for V with respect to a reference point. So why bother? What's the point in doing all this? Well, there is an advantage, and we'll be able to see it if we go back to the fundamental theorem of gradients. So what that says is if you have the integral of the gradient of a scalar function, dot dl, integrated over a path going from A to B, you simply get the answer that it's equal to the difference in the values of that function at those 2 points. And if we compare this equation to the very first one at the top of the page here, we see that the left-hand sides are the same, and that means that the right-hand sides have to be the same. So minus E is nothing more than the gradient of this new quantity V that we've defined. And that is the significance of this result. E is minus the gradient of V. And so this tells us that there's something special about an electrostatic field. It can always be written as minus the gradient of some scalar function. Now this is a nice compact vector expression. In Cartesian coordinates, what it really means is that we can get the 3 components of the electric field merely by taking derivatives of the potential with respect to x, y, and z. Of course, the minus signs are present as well. Let that sink in for a moment, because it suggests to us that if our ultimate goal is finding the electric field, which means finding the components of the electric field, one way to do it would be to first find the electric potential V and then simply take 3 derivatives. That's the punchline. What we've actually done by making this special definition of the electric potential is we've reduced a complicated vector problem, finding E for a charge distribution, to a simpler scalar problem, finding V for the charge distribution and then taking derivatives to construct E. And you'll see, after we develop a few more formulas, that finding V for a charge distribution is usually much easier because there's no direction involved. So that is the advantage in defining the electric potential. One note about the reference point that was mentioned on the previous page. The reference point is arbitrary because since it's an additive constant, it will not affect the components of E, which are obtained by taking derivatives. However, in most cases in electrostatics problems, we usually take that reference point to be infinitely far away from the charge distribution. And so that will often be assumed in problems dealing with electrostatics. There are certain exceptions, because sometimes that choice of the reference point leads to complications, and those are mentioned in the textbook. You'll also encounter them in at least one homework problem, so be on the lookout for that. All right, to take advantage of this simplification, having reduced a complicated vector problem to a simpler scalar problem, we have to come up with an apparatus for finding V. Let's assume that we know a charge density in a certain region of space. How can we find the electric potential in that region? And the starting point is Gauss's law in the differential form del dot E is rho over epsilon naught. Add to this the expression that relates E as minus the gradient of V. And so if we substitute E into Gauss's law, we get this expression, and the left-hand side is actually nothing more than minus del squared V. What we basically have is del dot del V, gradient of V, or del squared V. And that expression has a special name associated with a famous physicist of long ago, Poisson. This is referred to as Poissons Equation. And remember as you look at this that for compactness we have not written any functional dependence of V and rho. But remember that those two are actually functions of space. The charge density may vary with position, and indeed the electric potential will almost always vary with position in the vicinity of a charge distribution. So that's Poisson's equation, and a large part of the study of electrostatics is devoted to figuring out ways to solve it. In other words, if you know what rho is, how do you find V? There is one special case worth mentioning, and we will turn our attention to that equation in Chapter 3 in just a week or so. That is the equation that results from Poisson's equation if there's a region of space where there's no charge. So in a charge-free region, we get the rather simple-looking del squared V equals 0. And there are lots of special techniques for solving for V if we know that it satisfies this equation. But more on that, as I said, in Chapter 3. The only thing about Poisson's equation is that it kind of seems backwards. Let me just go back for a moment and show it to you, because it doesn't solve for V. Basically, Poisson's equation could be written as, given V, what's the charge density? You could solve this equation for rho rather easily. But usually we want to do the opposite. We want to know how to find V if we're given the charge distribution. So can we invert it? Can we find an expression for V in terms of rho? And of course, the reason I'm asking that question is because the answer is yes. To see how that equation comes about, let's consider a region of space near a point charge Q at the origin. And we'll assume this point charge is positive. So then what we'll do is evaluate the electric potential difference between 2 points, one at infinity, that's our reference point, and then one at a position vector r, away from the origin. And let's imagine that the path we use to evaluate this integral, to find the electric potential, is just a path along the radial direction. We know the answer doesn't depend on the path, so we can choose any path we want to, and this indeed is a simple path, as we'll see in a moment. So we know the electric field of a point charge is Q over 4 pi epsilon naught r hat over r squared. The point charge is at the origin, so these are just the regular printed r vectors. We also know, if we choose the radial direction for our path, that the dl vector can be written as dr r hat. Okay, it's in the r hat direction, and dr represents the differential change in the distance. So with those two plugged in to the integrand, E dot dl, well, we have a term with an r hat and a term with an r hat, so r hat dot r hat is 1, and what's left is minus q over 4 pi epsilon naught times the integral dr over r squared from infinity to r. And if we crank that out, we find that V is q over 4 pi epsilon naught r. So this is the electric potential in the vicinity of a point charge at a distance r away from the charge. Note, as I said before, that the electric potential is a scalar function. There's no direction associated with it, and indeed this result is special too because it only depends on the distance away from the point charge and not the particular theta or phi angle. So there's a nice simple expression. Well, we'd like to be able to use this or something like this to find V for an extended charge distribution. And one easy way to find that result is to imagine that we have a continuous charge distribution. We've seen this figure before. We carve it up in little chunks that have charge dq, and we'd like to know what the potential is out here at point P. So first, we use the differential version of the point charge equation and say what contribution to the electric potential would an element of charge dq give. And of course, that's going to be dq over 4 pi epsilon naught script r. The reason we use script r here is that the charge is not located at the origin, and so we just need the distance from the element of charge to the point P. Otherwise, all we've done is just taken the equation for the point charge and changed q to dq and v to dv. Well, if the charge distribution is made up of a charge per unit volume rho, then rho d tau is another way to write dq. And so dv is rho d tau over 4 pi epsilon naught script r, and we just integrate over the entire charge distribution, the volume of the charge distribution, to find the electric potential at that point. Now, it still may be a rather complicated integral to do, because rho could be a function of position. And obviously the script r vector changes as we integrate throughout the whole volume of the charge distribution. That distance changes. However, it's just a distance, and there's no x hat, y hat, or z hat terms that are involved in finding the electric potential. So generally speaking, it's easier to use this equation to find the electric potential at a point than it is to use something similar like Coulomb's law to find the electric field at that point, because there's no vector quantity involved. And if we can find an expression for V at some arbitrary point in space, taking derivatives of it with respect to x, y, and z will give us the components to the electric field. And we'll do some examples of this in class. Please also take a look at this section in the book. There's some nice examples there as well. See you in class.